Assalamu alaikum. In the previous lecture, we have covered the basics that includes the identification of variables. Second thing is this hardware elements. So today we will cover the main topic of the S1 exam, development of mathematical models. First of all, in basics, for any chemical process, we have three types of models. Models, or you can say the equation. Basically, these models here represents the dynamic behavior of the any chemical process with respect to the time. उसके different variables like temperature, density, pressure, volume, how they are changing with time. So in basics, the models classification is done into three types. One is known as the theoretical, another is known as empirical, and the last one is the semi-empirical, which is a combination of this theoretical and empirical. Theoreticals are basically depends on the basics laws of science, chemistry, physics, biology. Okay, mathematical models are developed on the basis of law of conservations. We have four laws of conservations. One is law of conservation of total mass. Second is the law of conservation of component mass within that total mass. Then comes the third is the law of conservation of energy. And the fourth one is the law of conservation of momentum. Momentum here means mechanical energy. So in this whole course we will consider the change in momentum 0 for simplification. So let's start with the first basic law of conservation. Law of conservation of mass. It says accumulation of mass of let's put A within the system rate of accumulation will be equal to the rate of mass of A entering into the system minus rate of mass of A leaving the system. Let's suppose if we denote M as a total mass having units kg and M in as rate of mass in, by definition we call it mass flow rate. As it is entering, so we call it mass flow rate in, and same mass flow rate out. Then we can develop a differential equation in which rate of accumulation will be represented by d over dt, means differential of mass divided by differential of time, means the mass within a system changing with the time is equal to, by law of conservation, mass flow rate in minus mass flow rate out. Now by the basic knowledge of chemical engineering, we can convert this equation into many other forms. The first form is to represent this equation in form of volume and volumetric flow rate. As we know that mass is equal to density into volume, where V is your volume, and mass flow rate in is equal to density into area in density into volumetric flow rate Q in, and also the mass flow rate out is equal to density into volumetric flow rate out, where Q in is volumetric flow rate in and Q out basically the volumetric flow rate out. So by inserting this equation, insert the above equation into A, just label this equation as A, then it will be equal to the density into rho into volume divided by D is equal to rho into Q in minus rho Q out. Now if density is constant, we can write the change in the volume within a system is equal to volumetric flow rate in minus volumetric flow rate out. Now in case if your system is gas, then gas will be leaving with some specific velocity. So if we have the inlet velocity represented by V, velocity of the gas in, and velocity of the gas out is represented by V out, where gas is your system, then you can convert volume into the volume you can convert this volumetric flow rate into velocity by formula volumetric flow rate is equal to cross-sectional area through which it is passing and entering into the system, cross-sectional area, into V. Now if the volumetric flow rate is in, then it will be velocity in. If your volumetric flow rate is out, then it will be cross-sectional area into the velocity that is leaving the system, of the gas that is leaving the system. So your equation is further modified as dV over dt is equal to area into V in minus cross-sectional area V out So here you can see you can have a different mathematical model equation depending upon the scenario for which you are solving the control problems. Now let's look into the law of conservation of energy. The law of conservation energy says rate of energy accumulation within a system is equal to the rate of energy in by convection minus rate of energy out by convection plus rate of addition of the energy to the system minus from surroundings minus rate of work performed on the system by the surroundings. So the total energy can be denoted by U. This is the total energy. It will be sum of your internal energy plus kinetic energy, Ke, plus potential energy. Within this whole course, the kinetic energy plus the potential energy will all be considered as zero, means it is neglected for simplification. Now the second term, rate of energy by convection. Okay, it will always be represented as mass flow rate into the specific enthalpy, where m is the mass flow rate and h is your specific enthalpy. So if the rate of energy by convection entering, then we can say it is equal to the mass flow rate in into the specific enthalpy in. Now if the rate of energy by convection is leaving, it will be equal to the mass flow rate out into enthalpy out. Last thing, that is the rate of heat addition from surroundings. It will be represented by Q. Now here to mention, if Q is positive, this means heat is adding. Now if Q value is negative, this means heat addition. It is not a heat adding, it is the heat consuming or leaving from the system. So overall, the net rate of work will always be represented by W of the shaft work. For example, in the car, a chemical engineer knows that by a chemical reaction of fuel gives us the chemical energy, which is converted into the mechanical energy and is given to the shaft of the vehicle, and then the vehicle or a car moves. In this whole course, we will consider, for simplification, that there is no rate of work performed on the system. So now you are putting all the symbols into the main equation. The simplified form will be the U internal over dt is equal to entering will be positive, mass flow rate in, specific enthalpy in, minus mass flow rate out, specific enthalpy out, plus Q if Q is adding, minus Q if Q is leaving. If you have a multiples, then it will be the net. Now for liquids, especially for the liquids, and we will be dealing only liquids here, you can say the change in internal energy can be related to the change in enthalpy, total enthalpy H, and this change in total enthalpy can be equal to the heat capacity into the change in temperature. Into the mass m, where mass is the total mass within the system. So now your equation will be modified as d mcp t over dt is equal to m in into H specific enthalpy in minus M out specific enthalpy out. Now the specific enthalpy in and the specific enthalpy out can be represented into their specific temperatures by a formula Cp d T in minus T some reference. This reference temperature also here T minus T reference. T reference. And the out will be equal to the Cp D T out minus T reference. So the equation will become d m Cp d T minus not D differential we have already written here T reference over dt is equal to the mass flow rate in into Cp T in specific enthalpy of in minus T reference minus mass flow rate out Cp out T out minus T reference plus Q. Now if your mass is constant, it can comes from out from the differential. Cp is also constant. Cp in and also the Cp out. If all these three are constant, then they can come out and represented by a specific C. And for simplicity, you can assume your T reference temperature as the 20 degree, or you can write as T reference as a 0 degree temperature. Here let T reference equal to 0 degree. Basically it is the T reference is your ambient temperature in which your system is placed. फॉर एग्जाम्पल अगर आपका वैसे 20 डिग्री पे पड़ा हुआ तो 20 डिग्री आपका रेफरेंस टेम्परेचर है. अगर आप अपने सिस्टम को 0 डिग्री पे रखें तो उसका 0 डिग्री टेम्परेचर है. सो नाउ योर ओवरऑल इक्वेशन विल बी इक्वल टू द m c d t over dt is equal to m flow rate in C T in minus m flow rate out C T out plus Q. Now you can further modify this equation by changing this mass, representing it into the rho into V. Also changing this mass flow rate and expressing it into volumetric flow rate rho into Q in, and converting this also rho into Q out. So your final equation will be equal to rho V dt over dt is equal to rho Q in T in minus rho Q out T out specific plus Q. Now it is to mention here this is the simplified form of the mathematical model representing the dynamics of energy, or you can say temperature, of the system. Let's do the last derivation, that is the law of conservation of component mass within total mass. The law says the rate of accumulation of component mass is equal to the rate of mass of component entering into the system minus rate of the mass component leaving the system plus rate of generation of component mass minus rate of consumption of component mass. So let's suppose your component mass is represented by MA, mass of component A, and mass flow rate of A will be equal to the mass flow rate of component A, M flow rate of A. If it is entering, then it will be in, and if it is leaving out, then it will be the mass flow rate of component A. Out means leaving the system. So in this case it will be equal to the d MA over dt accumulation is equal to the M flow rate in minus M flow rate out of component A plus minus consumption. So you can represent the generation generation G and minus consumption C. In case if the generation is because of the rate of reaction, then it can be correlate with the rate of reaction equation that we will do in the next lecture. And if it is consuming because of the rate of reaction, then it can be related, the consumption can also be related to the rate of reaction equation. So overall your equation will be rate of change of mass A within the system with the time is equal to mass flow rate A in minus mass flow rate output plus generation minus consumption. Now this equation can be related with the mass fractions. For example, mass of A can be a fraction of A into the total mass. Also, mass flow rate of A can be a fraction of total mass flow rate. So now let's go through to the presentations that will summarize our today lecture, and then we will move to the next lecture in which we will be doing some examples using these basics law of conservation, inshallah.